Well, hello, ladies and gentlemen. So today we're going to move on from the Brayton cycle gas turbine that we developed over the last couple of days. In fact, we've done quite a bit of examples. Well, we've done a fairly extensive example of a Brayton cycle complete with intercooling, reheating, irreversible compressors and pump and turbines. So remember, a gas turbine, the purpose of a gas turbine is to produce shaft power. Well, today we're going to look at a jet engine whose purpose is to produce thrust, not to produce an output W dot or a shaft power. The purpose is to produce thrust. So we're going to spend this period developing our knowledge of jet propulsion. So we'll look at a Brayton cycle-based jet engine. And these are used in jets. Turbojets are used in some applications. Most of them are turbofans that involve some shaft power. But we're going to look at a turbojet today, which is a device that doesn't produce any shaft power, but only produces thrust. Okay? So we'll talk about the layout of a jet engine. We'll talk about calculating the thrust produced by a jet engine, and then we'll do an example. Okay? Okay, so what's the layout of a jet engine? Well, a jet engine, the purpose of a jet engine is to produce thrust, in other words, to accelerate airflow or mass flow, thus producing some kind of thrust or reaction. So the purpose of a jet engine is not to produce shaft work, but to produce thrust. So here we have a diagram here. This is the front of the jet engine. We have the nacelle, or the encapsulated shell around the jet engine here. So this is the nacelle, or the shroud that is around it, the outside of the jet engine, if you like. And inside of it are several major components. First thing is, and let me draw a TS diagram as we go through and look at each and every device here. So we start off at the inlet. So the air is moving in this direction from left to right. So the inlet is at location 1 to the jet engine. So you're looking into the inside of the engine. You'll see a bunch of blades in there. You'll see a cone at the front. So you're looking into the front of the engine, and the air is moving in from left and going to the right. So the air moves in first into a diffuser. The purpose of diffuser, if you recall from our chapter on open flow devices, is to convert kinetic energy of the flow into a pressure rise and a temperature rise. So a diffuser the idea of a diffuser is to convert kinetic energy into internal energy and a pressure rise as a result. So in the diffuser, temperature and pressure go up, and the kinetic energy of the flow goes down. Now, if this is a reversible diffuser, so we have temperature and specific entropy. If this is a reversible diffuser, then starting off at state 1, going through the diffuser, temperature goes up, and if it's reversible and adiabatic, entropy is constant, so it's isentropic. So going through the diffuser, we have a temperature and a pressure rise from state 1 to state 2. So as the air goes through the diffuser, it's an isentropic compression process because pressure goes up, temperature goes up, and kinetic energy goes down. So that's what a diffuser does. It takes kinetic energy at the inlet flow and produces a pressure rise. So that's the purpose of a diffuser. Then we go through a compressor. Let's say the compressor is isentropic as well. So we go through, from state 2 to state 3, we go through a compression process. So here's the compression process. As you can see, we're assuming reversible diffuser and compressor at this point. If they were irreversible, of course, there'd be some slope to these process curves, all right? So the air passes through a compressor and pressure goes up, and we end up at state 3. So pressure goes up and temperature goes up as it goes through the compressor, okay? Then we pass the air through a combustor. It's a chamber in which fuel is injected and ignited. So we release heat in a combustor by burning fuel. And we assume to be doing this, presumably we're doing this isobarically, who knows? So here we have heat addition from 3 to 4 in the combustor, okay? So then we have hot air. So temperature goes up in the combustor. So we have very hot air, pressurized. And then we pass the products of combustion through a turbine, pressure falls, and if it's reversible, adiabatic, then entropy is constant. And entropy is constant. So we end up at state 5, which is the turbine exit. Now let me state here that we have a pressure. The pressures that are of interest in this cycle, of course, are the maximum pressure in the cycle. So we're interested in P max. We're also interested in the atmospheric pressure. So the pressure outside of the jet engine at the inlet and at the outlet, this is a pressure of interest as well. So we're also interested in the local atmospheric pressure, which is equal to P1, and the outlet, which is P6. Okay, so we're interested in the local atmospheric pressure outside of the jet engine. So once the airflow leaves the turbine, it then gets accelerated through a nozzle. So we have a nozzle here. You can see the areas, the flow areas constricting. So we're taking internal energy and pressure work and converting it into kinetic energy and accelerating the flow as it moves out the back. So we have a temperature and a pressure drop. So temperature goes down in the nozzle, pressure goes down in the nozzle, and kinetic energy goes up. So we have, if it's reversible in an adiabatic nozzle, then we have an isentropic expansion process in the nozzle. So we're accelerating the flow by letting it expand, okay? Pressure falls, temperature falls, so we're expanding it and allowing it to accelerate, okay? So this is the TS diagram for an ideal jet propulsion cycle. So this is for an ideal jet propulsion cycle. If the compressor, the turbine, the nozzle, the diffuser are not ideal, in other words, they are irreversible, then all of these process curves would have some sort of a positive delta S. Okay? But let's keep things a little bit simple. Let's just keep things simple. Let's just keep things simple, okay? Okay, now one thing to notice about the jet engine here, it doesn't produce any network. W dot shaft for the whole thing is 0. There's no shafts leaving the nacelle. Air is going in, hot products of combustion are going out. So there's no shaft power produced, net shaft power produced by the jet engine. That means that W dot of the compressor, so W dot compressor is equal to W dot turbine. The turbine is driving the compressor and there's no work or power left over. So when you're doing these jet engine problems, unlike the gas turbine problems we did previously, W dot net is 0. The turbine drives the compressor. There's nothing left. Okay, this is purely a thrust-producing device. Now, by the way, those of you that like jet engines or are interested in aerospace, jet engines aren't really used as much as they used to be. In the early days of jet propulsion, even passenger jets, commercial airlines used jet engines. Today, to increase efficiency, they use what are called turbofans. Turbofans put a big fan right out here in the front, a big fan, and they actually do produce net shaft power to drive a big fan, or in the case of a turboprop, a big propeller. So, but we're going to make our life easy here and just look at jet propulsion. There's no fan, there's no propeller out here. It's just using the acceleration of the flow to produce thrust. Now let's take a moment here to calculate what the thrust is. How would we go about calculating the thrust produced by this jet engine? So here we have the nacelle. So air comes in. So this is the inlet, and this is the outlet. Okay, so I have an inlet mass flow, m dot in. I have an outlet mass flow, m dot out. Presumably they're about the same. M dot for the fuel is typically quite low. So m dot air is basically m dot in and m dot out. So we have a velocity at the inlet, and we have a velocity at the outlet, or an average velocity, let's say, for the flow at the inlet and outlet. So how do you calculate the thrust? So the thrust, so typically, to produce thrust, the outlet velocity has to be greater than the inlet velocity. So the outlet velocity is greater than the inlet velocity, and that produces a reaction. That produces a reaction to retain or maintain the position of the jet engine. So this is our jet engine, okay? Okay, so we have a reaction here, or F reaction if you like. So we have F reaction equals F thrust. And the equation for thrust produced by the jet engine, so F thrust is equal to the change in momentum flux in the horizontal direction. So we have m dot out, velocity out, minus m dot in, velocity in. So here's your expression for the thrust produced by the jet engine. Now you can get this equation. If you're interested, you can get this equation by applying the Reynolds transport theorem to momentum. We've applied the Reynolds transport theorem to entropy, mass, and energy, total energy. You can apply the Reynolds transport theorem. This is an open system. We have mass flows here. So our system is the entire jet engine here. It's an open system with a single inlet, single outlet. So you apply the Reynolds transport theorem to momentum, single inlet, single outlet. The only forces on the control volume are the reaction force, and you get a simple expression for the thrust. Okay? So what this means is for any given m dot, the greater the outlet velocity compared to the inlet velocity, the greater the thrust. So what this says is, as the difference between the outlet velocity minus the inlet velocity, as this goes up, thrust goes up. So as you increase the outlet compared to the inlet velocity, you accelerate the flow, you get an increase in thrust. It also says that as you increase the mass flow rate, m dot in and m dot out, as you increase the mass flow rate, or if you just like m dot, you increase the mass flow rate, as that goes up, thrust always also goes up. Okay, thrust also goes up. Okay, simple jet engine. Pretty simple TS diagram. If we have irreversible processes going on, then we would have to do isentropic efficiencies and all that, and it would make our life a little bit more complicated, okay? All right, let's stop here for a minute and we shall do an example. Okay, let's do a problem here. We have a jet engine. So this is a turbojet with reversible adiabatic nozzle and diffuser. Okay, so if we apply the entropy balance to the nozzle and diffuser, it means isentropic. The inlet temperature and pressure and velocity at the inlet of the engine are 241 Kelvin. The local atmospheric pressure, that means this thing is operating at high altitude. The local atmospheric pressure is not 100 kPa, but 32 kPa. So that we're at a third of an atmosphere. The local atmospheric pressure is about a third of an atmosphere. So we're at high elevation, high altitude. The plane is traveling at a speed of 320 meters per second. So the intake air velocity is 320 meters per second, okay? The compressor pressure ratio is 12. The compressor isentropic efficiency is 80%. So this is an irreversible compressor. The maximum temperature in the cycle, that's the, so let's see, let's have our diagram here. Diffuser, compressor, combustor, turbine, nozzle. So here's our device diagram. The peak temperature in the cycle, which is the combustor exit temperature, is 1400 degrees. The isentropic efficiency for the turbine is 80%. And the pressure at the outlet of the nozzle is the local atmospheric pressure, so that's 32 kPa. And the mass flow of air flowing into and presumably out of the turbojet is 40 kilograms per second. And we're going to do this problem. We're going to work this problem. I'll show you what we're going to find in just a moment. We're going to assume constant specific heats for this problem, evaluated at room temperature or 300 degrees Kelvin. In other words, we're going to assume cold air properties. Cold means 300 degrees Kelvin. Cp is 1.005 kilojoules per kilogram degree Kelvin. And the ratio of Cp to Cv is 1.4. Okay, so these are cold air, constant specific heats we're going to assume when we work this problem. So what are we going to find here? We're going to find the power, the compressor power, W dot compressor. We're going to find the turbine power, W dot turbine. We're going to find the rate of heat addition in the combustor, Q dot combustor. We're going to find the outlet velocity of the exhaust or the air, if you like, hot air or hot exhaust, coming out the tail of the jet. We're going to calculate the resulting thrust. And then, unlike in previous problems, we're going to figure out how much fuel is actually being burned, injected and burned in the combustor. So we have to inject fuel into the combustor. It gets burned and release heat. We're going to actually calculate what the fuel flow rate is, m dot fuel. Now, to do this, I've looked up in tables, and you can go to the very back of the notes. I've looked up in tables, I've looked up what's called the heating value. HV. HV is the heating value for the fuel. It's the amount of heat released when you burn the fuel with enough air. You burn all the fuel. How much heat is released? And I get 42.7 megajoules per kilogram of fuel. So if I know the heat transfer rate required in the combustor, Q dot combustor, in theory I can use the heating value to calculate the amount of fuel being injected to produce that heat release. And we'll take a moment then when we're done to compare the amount of fuel burned to the mass flow of the air. We'll find out that the mass flow of the air is typically much larger than the m dot for the fuel. So it's probably a pretty good assumption in all of these Brayton cycle, gas turbine, jet engine problems to assume that mass flow is essentially constant throughout the entire device. You'll see that m dot for fuel is on the order of only a couple of percent of m dot of the air. So we can assume that the mass flow rate through this device is essentially m dot air all the way through, okay? Let's put up the TS diagram here before we get too excited and before we start cranking out results here. Let's put up the TS diagram. So here's temperature, specific entropy. So we're told that these are reversible adiabatic nozzles and diffusers. So I start off at state 1. If it's a reversible adiabatic compression process in the diffuser, reversible adiabatic, you apply the entropy balance and you get S dot gen is 0, so it's reversible. And there, I'm sorry. You get reversible adiabatic compression in the diffuser. Therefore, you get isentropic. Get an isentropic process through the diffuser. So here's state 2 as we pass through the diffuser. Temperature goes up, pressure goes up in the diffuser. We convert kinetic energy into enthalpy. And then we have an irreversible compressor with an isentropic efficiency of 80%. So we get up here to P max. So this is our P max right here. So here's the real process from 2 to 3. Of course, here's the isentropic process from 2 to 3 sub s, okay? Isentropic process will be of interest when we try to calculate the compressor power. And then we have heat addition up to a maximum temperature, T4. So here's the heat addition, Q in the combustor. Q in the combustor. That's occurring from 3 to 4. And then we have expansion in the turbine. Expansion from 4 to 5. Of course, here's the isentropic process. Here's 5 sub s. And then we have reversible adiabatic, therefore isentropic expansion in the nozzle. So the nozzle converts enthalpy into kinetic energy, and we have an outlet increased flow velocity. So this is state 6, okay? And these are all adiabatic except the combustor, okay? So there's the TS diagram right there. Notice that state 1 and state 6 both are at atmospheric pressure. So P1 equals P6 equals the local atmospheric pressure, okay? Local atmospheric pressure. Okay, let's get started. Let's get started then. Let's get started. Oops. Analysis. Analysis. Let's calculate the compressor power. Let's calculate the compressor power. So to get the compressor power, I need to know something. I need to apply the energy balance from state 2 to state 3. Or I can also use the definition of isentropic efficiency. Maybe I should go that way. Let's see here. So the definition of isentropic efficiency for the compressor is equal to W dot for the isentropic compressor divided by W dot for the real compressor. So W dot for the real compressor is equal to W dot for the isentropic compressor divided by the isentropic efficiency for the compressor, okay? I have the isentropic efficiency, check, but I don't have W dot for the isentropic compressor. By the way, this is equal to M dot times the specific work for the isentropic compressor divided by the isentropic efficiency. Now, if I apply the energy balance, for process 2 to 3 sub s, the isentropic efficiency, the isentropic specific work for the specific work for the isentropic compressor is going to be equal to H3 sub s minus H2 if I apply the energy balance, okay? Neglecting changes in kinetic and potential energy. Okay? Now the problem is I don't know any of this stuff. I don't know H2 and I don't know H3. Let's see if we can get H2. Let's see if we can get H2, and then we'll worry about H3. Let's look at the process. Let's look at the process 1 to 2. Let's look at the process 1 to 2. That's the reversible adiabatic, therefore isentropic compression in the diffuser. So let's look at process 1 to 2. And this is isentropic compression in diffuser. Isentropic compression in the diffuser. Okay? Let's apply the energy balance to our diffuser. So our diffuser looks something like this. We have our inlet. The area opens up. So here's the inlet at state 1. Here's the outlet at state 2. At the inlet, we have some velocity at the inlet. Of course, we have a temperature too. We have a T1 and a P1. And at the outlet, I have a T2, I have a P2, and I have an outlet velocity, VEL2. Now, the purpose of a diffuser is to convert the kinetic energy of the flow into enthalpy. So I'm going to assume that the outlet velocity of my diffuser is negligible. Negligible compared to VELN. So I'm going to assume for the diffuser, the kinetic energy at the inlet is much, much greater than the specific kinetic energy at the outlet. Essentially, the diffuser does its job and converts kinetic energy into enthalpy. So I'm not going to, in my calculations, this VEL2 is not really going to come up. I don't know what it is. So I'm going to neglect the kinetic energy and the effects of velocity at the outlet. Let's apply the energy balance. Let's see here, E balance. Let's see here, it is an insulated, it's an insulated device, this diffuser. So there's no heat transfer, there's no shaft power, there's no shafts in there. I'm going to neglect changes in height or elevation. So what? Q dot minus W dot is equal to dE CV dt. I'm only going to write this once. We won't do it for the nozzle. The nozzle has a similar analysis. And then I have sum of m dot out minus the sum of m dot in, okay? No heat transfer, no work, steady state. There's no indication this is an unsteady problem. I'm going to neglect changes in height or potential energy. There's no indication about a height change contributing to any energy changes. And so I'm going to have on the outlet m dot out H2, that's the outlet. And then I'm neglecting the kinetic energy at the outlet. So that's going to be all there. And then on the inlet, I have m dot, I'm not going to do out, I'm just going to do m dot 2 and m dot 1. I have H at the inlet plus the kinetic energy. I can't neglect kinetic energy at the inlet. The purpose of the diffuser is to convert kinetic energy into an enthalpy change. So I have to have the inlet kinetic energy term. So I have KE1. So I have H2 is equal to H1 plus the specific kinetic energy at the inlet. What happened to the mass flow rate? I'm assuming m dot 1 is equal to m dot 2, so I got rid of the mass terms. Let's see here, what's H1? Well, actually, we're not going to worry about that quite yet. Oh, this is a constant specific heat problem. Ooh. Well, that means that this is equal to Cp T3 sub S minus T2. Okay. So I want to find T2, not H2. So this is a constant specific heat problem. So this implies T2 is equal to T1 plus the specific kinetic energy at the inlet divided by Cp, using a property relationship. Delta H is equal to Cp delta T for constant specific heats. So I just use the property relationship and immediately have an expression for T2. I have T1. Let's see here. T1 is 241 degrees Kelvin. I have Cp as well. The specific kinetic energy at the inlet. Oh, well, I guess I need to work on that. Let's see here. T2 is equal to T1, and I'll expand the kinetic energy term. That's 1/2 velocity 1 squared over Cp. I have the inlet velocity. The inlet velocity is 320 meters per second. So let's plug in here. Let's plug in here. We got 241 degrees Kelvin plus 1/2 320 meters per second squared divided by Cp, which is 1.005 kilojoules per kilogram degree in Kelvin. One little thing here, the kinetic energy term will have units of meters squared per second squared, which is a joule per kilogram, not a kilojoule. So I have to convert this from joules. So there's 1,000 joule per kilojoule. So I have to convert the kinetic energy term from joules to kilojoules so the unit matches on my Cp. So let's see here, the joules will cancel out with the kilogram and the joules here. The kilojoules will cancel out there, and I'll have 1 over Kelvin. And so the unit on this term is going to be a Kelvin. Let's see here. So I have a temperature T2. Let's see what my temperature T2 is. 291 degrees Kelvin. 291 degrees Kelvin. 291 degrees Kelvin. I'm going to put this actually in my TS diagram. Let's see here. T1 is equal to 241, and T2 is 291 degrees Kelvin. Okay? So going through the diffuser, we pressurize the flow. We'll show the pressure rise in a moment. And we've heated up the flow by converting the kinetic energy into enthalpy, internal energy, and pressure work. Okay, so pressure's gone up, temperature's gone up, pressure's gone up too, by the way. Pressure's gone up too, by the way. Let's calculate the pressure P2. Let's actually calculate the pressure P2. Let's just do that real quickly. So process 1 to 2 is isentropic. So that means I can use the isentropic property relationship. I can use the isentropic property relationship to get P2. What's the pressure rise associated with the diffuser? Let's have a look here. Let's go to, let's go to our nice property table. Isentropic process, variable specific heat, constant specific heat. Let's see here. T final over T initial is P final over P initial, K minus 1 over K. Okay, let's use this property relationship, constant specific heat, to get our final pressure P2 out of the nozzle. Let's see here. We have T2 over T1 is equal to P2 over P1, K minus 1 over K. So pressure P2 is equal to T2 over T1 to the K over K minus 1 power. And then I have P1 here. I have T2, I have T1, I have P1. Let's see here. T2 is 291 degrees Kelvin. T1 is 241 degrees Kelvin. K is 1.4, and then I have a 1.4 minus 1. And pressure P1, let's see, the inlet pressure at my diffuser. Oops, sorry about that. Wrong screen. Isentropic property relationship over there in the right-hand corner. So we're going to calculate the pressure P2, which is the diffuser exit pressure. We're going to calculate the pressure right here at the exit of the diffuser. The inlet pressure is 32 kPa. That's the local atmospheric pressure. So I have 32 kPa. And so I get P2. Let's see what the pressure P2 is. Be interesting to know. What's the pressure P2? 62.6 kPa. So I've doubled the pressure of the flow. So the pressure here at the outlet, so the temperature here at the outlet of the diffuser, T2 is 291 and P2 is 62.2. Okay? So the diffusers raise the pressure and raise the temperature. Okay, so what are we trying to do here? What are we trying to do here? So here I put the temperature and pressure at the outlet of the diffuser. So what are we trying to do here? We're trying to find the compressor power. So we need to find T3 sub S. T3 sub S to get the compressor power. Okay, well, let's apply let's have a look at the process 2 to 3 sub S. Let's have a look at the process 2 to 3 sub S. Now I know something about state 2. Let's do 2 to 3 sub S. 2 to 3 sub S. That's the isentropic compression in compressor. Not the real compressor, the reversible compressor. Reversible, REV, okay? So it's isentropic. So that means the following. T3 sub S over T2 is equal to P3 over P2 to the K minus 1 over K power. Oops, make sure I got that right. Sometimes I get the exponents wrong. Let's see here. Yes, K minus 1 over K. Now this pressure ratio, P3 over P2, is the pressure ratio for the compressor. R sub P for the compressor. Let's see, do we have that? R sub P for the compressor is 12. So the compressor pressure ratio is 12. It's increasing the pressure by a factor of 12. So I got this. So this is R sub P for the compressor to the K minus 1 over K power. Now I have R sub P. I have the K's, of course. I have T2. I just calculated T2. What was it? 291. So I can calculate T3 sub S. T3 sub S is equal to T2 R sub P to the K minus 1 over K. Let's see here, 291 degrees Kelvin. That's the compressor inlet temperature. Compressor inlet temperature. T2 is the compressor inlet temperature. And I have a compressor pressure ratio of 12. And K is, of course, 1.4. So I'm in good shape. So I have 12 to the 1.4 minus 1 over 1.4, and I get a T3 sub S. Let's see what our T3 sub S, 593 degrees Kelvin. It's actually 594. 594 degrees Kelvin. Check. I have CP, I have T3, I have T3 sub S, I have T2, excellent. I can calculate the compressor power now. Let's see here. Actually, let me put this temperature in T3 sub S, 594. I'm going to put that in. I'm going to put that in my diagram. Let's see here. T3 sub S, 594. 594. Okay, I might need that. Who knows? Who knows? Okay, so the compressor power, so I have m dot Cp T3 sub S minus T2 divided by the isentropic efficiency of the compressor. So that's equal to 40 kilograms per second. T3 sub S is 594 minus T2, which is 291. Degrees Kelvin, and then the isentropic efficiency is 80%. And I get a compressor power. I'm gonna have to crank this out. Let's see here. Compressor power. Oh, I forgot the CP. Forgot the CP. Ah, I just realized that. 1.005, and that's going to have units of kilojoules per kilogram degree Kelvin. Okay, so 40 times 1.005 times 594 minus 291 divide by 0.8, and I get 15.2 megawatts. 15.2 megawatts. 15.2 megawatts. That's pretty big. So W dot compressor. W dot compressor is 15.2 megawatts. I can write this somewhere. W dot compressor, 15.2 megawatts. 15.2 megawatts, okay? Now, what's W dot for the turbine? What's W dot for the turbine? What's W dot for the turbine? So that's the next thing we're supposed to find. Well, notice that the turbine drives the compressor. So that means the output of the turbine must be equal to the output of the compressor. So that's an easy one. W dot, so note, W dot compressor equals W dot turbine. Note, turbine drives compressor. So W dot turbine equals W dot compressor, which is 15.2 megawatts. Okay, it's 15.2 megawatts. So I'm going to write right over here W dot compressor equals W dot turbine, and they're both equal to 15.2 megawatts, okay? Okay, 15.2 megawatts, that sounds good. Let's calculate Q dot for the combustor. Let's calculate Q dot for the combustor. Let's calculate Q dot for the combustor. How much heat has to be added in the combustor, okay? Well, let's see here. So if we apply an energy balance to the combustor, we get Q combustor is equal to M dot times H at the inlet minus H at the outlet. So H4 minus H3. We apply the energy balance for the combustor. H4 minus H3. Now I have M dot, that's 40 kilograms per second. We're assuming the mass flow rate's constant throughout the device. M dot fuel is quite small. We'll show that in a bit. Okay, so I've got M dot. H4, well actually we're assuming constant specific heats. So this is equal to M dot Cp T4 minus T3. Now I have M dot, I have Cp. Do I have T4, which is my combustor outlet temperature? Let's see if I have T4, which is my combustor outlet temperature. Yes, the maximum temperature in the cycle, or T4, I have that. So T4 equals 1400 degrees Kelvin, okay? So I've got T4, that's done. Check. Now, what I don't have is T3. So how am I going to get T3? Well, how about we apply the energy balance to my turbine and see if I can get the turbine outlet temperature, which is my, compressor outlet temperature, which is my combustor inlet temperature. So let's look at process 2 to 3. This is in the compressor. This is through the compressor. So it's an adiabatic compressor, or at least I'm assuming it's an adiabatic compressor. So here we have our compressor. I'm assuming it's adiabatic. That's why I put the crosshatches here. So there's no heat transfer. So apply the energy balance, neglecting kinetic and potential energy changes. I get W dot, so E balance. I get W dot compressor is equal to M dot H3 minus H2, or assuming constant specific heats, M dot Cp T3 minus T2. So let me solve for T3. T3 is equal to W dot compressor divided by M dot Cp plus T3. I'm sorry, T2. T2. Now, I have W dot compressor. I just calculated it. I have M dot, I have Cp, and I also have T2 when I analyze the diffuser. T2 is 291 degrees Kelvin. I got everything. Let's see here. So, 15.2 megawatts. 15.2 megawatts divided by 40 kilograms per second. And then I have Cp, which is 1.005 kilojoules per kilogram degree in Kelvin. And then I have T2, which is 291 degrees Kelvin. Let's see here, megajoule. There's 1,000, kilowatts per megawatt. So I'm going from mega to kilo here. And that'll cancel out, and the kilowatts will cancel out with the kilojoule per second. And then the kilograms cancel out here. And I get 1 over Kelvin. So Kelvin goes upstairs, and that term has units of Kelvin. Let's see here, 15.2. 15.2. Let's see, 15,200 divided by 40 divided by 1.005 plus 291. And I get 699 degrees. I'm sorry, 669 degrees Kelvin, okay? So T3 is 669 degrees Kelvin. I'm going to put that in my diagram here. I might need that later. So T3 equals 669 degrees Kelvin, okay? T3 is 669 degrees Kelvin. And now I can calculate the heat transfer because I have the combustor inlet temperature T3 now. Okay, let's see here. 40 kilograms per second, 1.005 kilojoules per kilogram degree in Kelvin. And now I have T4, which is 1400 minus 669 degrees Kelvin. Kilojoules per second, this is going to have units of kilowatts. I'll probably convert that into megawatts here. And I have 29.4 megawatts. 29.4 megawatts. 29.4 megawatts. So Q dot combustor is 29.4 megawatts. Q dot combustor, 29.4 megawatts. That's a lot. A lot of heat. A lot of heat getting dumped in. 29.4 megawatts, 29.4 megawatts. Okay, so we got Q dot combustor, W dot turbine, W dot compressor. Let's find the outlet velocity. Let's find the fuel flow rate. Let's do that. Let's figure out how much fuel is burned in the combustor. Now remember, we have the heating value for the fuel. It's probably kerosene, basically diesel, a lighter diesel. The heating value is 42.7 megajoules per kilogram of fuel. So let's calculate M dot for the fuel. Let's do that. Let's calculate M dot for the fuel. Let's calculate M dot for the fuel. So M dot fuel. Well, what's that equal to? Well, first of all, I'm going to write out what the heat transfer rate is, Q dot combustion. Q dot combustion is equal to mass flow rate for the fuel times the heating value. Mass flow rate for the fuel is kilograms per second of fuel. The heating value is energy per kilogram released due to combustion. So that means M dot for the fuel is equal to Q dot from combustion divided by the heating value for the fuel. Now we have Q dot combustion is 29.4 megajoules. Watts, sorry. And we have the heating value, which is 42.7 megajoules per kilogram of fuel. 42.7 megajoules per kilogram of fuel. Of course, a megawatt is a megajoule per second. So the megajoules cancel out, and I get kilogram per second of fuel. Kilogram per second of fuel. So 29.4 divided by the heating value, I get 0.69 kilograms per second. 0.69 kilograms of fuel per second. Okay? 0.69, basically 0.7. Basically 0.7. So m dot fuel. Oh, I'm starting to run out of space. I think I better erase a few things. Not enough board space with this arrangement. Okay, so m dot fuel equals 0.69 kilograms of fuel per second. Okay? By the way, 0.69 kilograms per second of fuel compared to 40 kilograms per second of intake air. Now you see why we assume m dot through the device is constant, the same in the diffuser, compressor, combustor, turbine, and nozzle, because m dot required to burn, m dot of fuel required to heat up the air is so small compared to the airflow rate. So we're a difference of about 1%, 1.5% variation. So the m dot going through the turbine and the nozzle is about 1.5% higher than going through the diffuser, the combustor, and the compressor. Who cares? Who cares? That's why we're assuming m dot is the same all the way through. Okay, let's calculate the outlet velocity, VEL6. Let's calculate the outlet velocity, VEL6. Then we can get the thrust. Let's apply the, let's look at the process through the nozzle. So through the nozzle, we're looking at process 5 to 6. Process 5 to 6 through the nozzle. I want the outlet velocity, VEL6. Okay? So we look at process 5 to 6. And that is adiabatic, reversible, and therefore isentropic expansion in nozzle. Okay? First of all, if I apply the energy balance, no heat transfer, it's adiabatic, reversible, no heat transfer. I don't see any shaft work, so let me draw a little picture of the nozzle here. Let me draw a little picture of the nozzle. So here's our nozzle. So state 5, which is the nozzle inlet, state 6, which is the outlet. I want VEL out, which is VEL6. That's what I'm looking for, okay? So apply the energy balance to this thing, open system. No heat transfer is assumed to be adiabatic. No work going on. The point of a nozzle is to accelerate the flow. So the kinetic energy at the outlet compared to the specific kinetic energy at the inlet, we're assuming that the outlet kinetic energy is much greater than the inlet kinetic energy. So we're going to neglect the inlet kinetic energy. After all, nozzle is supposed to increase significantly the kinetic energy of the flow. So when I get my energy balance here, I'm going to get 0 is equal to m dot, and then I have h out, which is h6, plus ke out, which is ke6, minus m dot h5, and I'm neglecting the kinetic energy term at the inlet. So that's why we're missing the kinetic energy term at the inlet, okay? So on these nozzle and diffuser problems, you should neglect the kinetic energy somewhere. For the diffuser, you should neglect the kinetic energy at the outlet. For the nozzle, you should neglect the kinetic energy at the inlet. Okay? Now, of course, ke6 is 1/2 velocity 6 squared. Okay, so let's see. The mass flow rates are the same going in and out. So what I really have here is KE6 is equal to H5 minus H6, which of course is equal to CP T5 minus T6. Okay? Specific kinetic energy, again, is 1/2 velocity 6 squared. So let me put the 1/2 over on the other side of the equation and take the square root. So I get velocity 6 is equal to the square root of CP over 2 T5 minus T6. Okay? Now, one little thing to be careful of here, we'll show this in a minute. The CP has units of kilojoule per kilogram degree Kelvin, whereas I want it to have units of joules per kilogram degree Kelvin to get velocity here instead of velocity with some weird unit. Velocity in meters per second, not square root of kilometers per second or such, okay? Okay, so I clearly have to get some quantities here. I have to get T5 and T6. I don't think I'm going to go through too many of the details on T5 here, how we get T5. Suffice to say, I can apply the energy balance from 5 to 6, noting the isentropic efficiency of the turbine. So 5 to 6 is the turbine expansion process. I can apply isentropic efficiency to the energy balance, and I can get an outlet temperature, T5. Let's see, so I apply the energy balance to the compressor here, to the turbine, and I get, let's see, do I have a T5? Yes, I have a T5 and it is 1,022 degrees. 1,022 degrees. So I can get, note T5 equals 1,022 degrees Kelvin, and that's from E-balance process 4 to 5, okay? That's pretty easy to do. So I got T5, just from the energy balance on the turbine. I know the turbine work. Okay, I know T4, so I can get T5. Okay, now I need to get T6. Well, I know it's an isentropic process, 5 to 6. So 5 to 6 is isentropic. So that means T6 over T5 is equal to P6 over P5, K minus 1 over K from the isentropic property relationship. In other words, T6 is equal to T5, P6 over P5, K minus 1 over K. Now, I know T5, 1,022 degrees. I know P6. P6 is the outlet pressure at my nozzle, which is the local atmospheric pressure. Oops, I forgot to switch this again. Damn. So sorry about that. So I got T5, 1,200 degrees, 1,022. T6 is what I need to get now to get the outlet velocity. So I apply the isentropic property relationship to my isentropic acceleration expansion in the nozzle. T6 over 2.5 is P6 over P5, K minus 1 over K. Solve for T6. I have T5, which is 1022. I have P6, which is the outlet pressure of my nozzle, which is the local atmospheric pressure. So P6 equals P local atmospheric, which is 32 kPa. That's given here. 32 kPa, all right, good. So I got P6. Now I don't have P5. Oh boy, how do I get P5? Well, I could apply the isentropic property relationship to the turbine. I could apply the isentropic property relationship to the turbine. If I know the pressure in the combustor, then I can, and I know the temperature drop across the turbine, I can use a property relationship to get the pressure drop from the temperature drop and get P5. So I'm not going to go through the details here, but P5, let's see if I have it here. P5 is 197 kilopascals. P5 is 197 kPa. And how might I get that? Use Isentropic relationship for process 4 to 5. That's in the turbine. I know the maximum temperature, the turbine inlet temperature is, it's like what, 1400, 1200 degrees. I know the outlet temperature, T5, so I can get the pressure drop across the turbine, and therefore I can get P5. Okay? So I have everything here. Let's see here. I plug in, starting to skip some stuff here, but I want to get this finished up. T6, what is T6? 607 degrees Kelvin. 607 degrees Kelvin. Now I have everything. Oh boy, okay. So square root 1.005 kilojoules per kilogram degree in Kelvin. Divide by 2. And then I have T5, which is 1028 minus 607 degrees Kelvin. The Kelvins cancel out. Be careful here. I need to convert this from kilojoules per kilogram into joules per kilogram. So I have 1,000 joules per kilojoule. If I don't do that, then I don't get meters squared per second squared. When I take the square root, I don't get meters per second squared. So I get the outlet velocity of 913 meters per second. 913 meters per second. So the outlet velocity, VEL6, 913 meters per second. Oh boy, running out of space. VEL out, 913 meters per second. I can't read that, you can't read that, but it's right there, okay? Let's calculate the last thing, which is how much thrust this thing produces, and then we will be done. Let's calculate the thrust. Let's calculate the thrust. So we have our jet. Here. We have VEL in. We have M dot in. We have VEL out. We have M dot out. They're pretty much the same. So M dot in and out are both 40 kilograms per second. That's M dot for the air. The inlet velocity is 320 meters per second. That's a given. And the outlet velocity, which we just calculated, is 913 meters per second. Let's calculate the thrust. Let's calculate the thrust. Ooh, do I have the right screen on? Good. Yes, I do. So F thrust. These M dots are the same, so note M dot in equals M dot out, which is just equal to M dot. So F thrust is equal to M dot for the air times the difference between the outlet and the inlet velocities. Okay, so, whoops, getting a little fast here. VEL out minus VEL in. VEL out, of course, is velocity 6, and velocity in is VEL1. So I get 40 kilograms per second times 913 minus 320 meters per second, and I get a total thrust of 2.37 what? Let's have a look here. Well, let's just crank it out. So 913 minus 320 times 40. And I get 23720. Let's look at the unit on that. Let's look at the unit. So that will be kilogram meter per second squared. Kilogram meter per second squared is a Newton. Convert that into a kilonewton, I get 23.7 kilonewtons. So the thrust this thing produces, the thrust, F thrust, is 23, almost 24 kilonewtons. 23, 24 kilonewtons. F thrust equals 23.7 kilonewtons. Okay, kind of a long problem here. Didn't mean to take it so long. A lot of detail going on in this problem. So this thing producing a fair amount of thrust. Take care, ladies and gentlemen.